So in this lecture, we are going to actually discuss about what vector spaces typically are. This is obviously going to be a short video where we just introduce the concept of a vector space. So a vector space. So on a general, or I should say on a literal basis, we are pretty acquainted with the fact what vectors are typically, right? So we know that if you simply consider an R2 plane, so suppose you have the R2 plane like this, so it's y, it's x. Suppose you have a point here, say xy, a coordinate xy, then you can generate a vector of this sort. So that's typically a line which has a direction and two endpoints. To be precise, one fixed endpoint, if I say. So in this case, that's the origin. And this vector is completely characterized by the coordinate, which helps in directing this line. And the ordinary way of denoting this vector is by saying it's a vector of the type xi cap plus yj cap. Like this is simple plus two level discussion. This is simple plus two level discussion. Right? So xi cap plus yj cap, where I cap actually denotes the unit vector in the x direction, and it's just the coordinate 1 0 in the x direction, in the positive x direction, and j cap precisely denotes the coordinate 0 1 in the negative x direction, in the positive y direction. So suppose this is the point 1 0 and this is the point 0 1. So these are the very basic mathematical concept related to what vectors are typically on a physical plane. And if I just simply consider the concepts or the mathematical properties related to a vector, we know that if there are what should I say? Yeah, there are pretty well defined addition and scalar multiplication defined on vectors. That is, we can obviously add two vectors, right? We can add two vectors. Suppose this is v cap, v1 vector. This is v2 vector. We can add these two vectors to get a resultant vector. Then we can scale a vector by just having a constant multiple on it, right? Suppose this is the vector v cap. If I multiply it with a certain constant, say c, then I'll get a scaled vector which is cv cap. Right? So our goal is to simply construct a certain structure which carries the properties of what vectors are on a physical plane, and in some way it's a generalized concept of what vectors are. Okay, so to do that, what we actually need is a well-defined additive operation which has the properties of representing an identity vector, an associativity of the associativity of the addition axiom or the addition property. Then you have the inverse of a vector, that is inverse of a vector in the sense that if you have this as the v vector, then if you direct it in the opposite sign, keeping its magnitude same, then you simply get minus v vector, right? If you add v vector and its opposite vector, then you get what we call the null vector, right? The null vector, which has no magnitude typically speaking, right? And obviously the vector addition is commutative, right? It doesn't matter from which way you add two vectors. So this brings us to the concept of a vector space, where we say that let V be a non-empty set, and let plus be a binary operation, be a binary operation defined on V, defined on V with the following properties, with the following properties. Okay, a binary operation typically means that this operation is, or I should say this non-empty set is closed under this operation. So so the properties are: number one, that is, for all A, B, C in the non-empty set V, A plus bracket B plus C is same as A plus B bracket plus C. Right? So this is the associative operation. Right? So it does not matter in a linear addition, which elements you group first to add. Okay, which pair of elements you group first to add. Okay. Number two is that there exists an element 0 in V such that when you add any element from V to 0 from either side, you get the same element back. Okay. This element 0 is called the additive inverse, additive identity of the non-empty set V. Okay. To be very specific, this 0 is actually used as a symbol. Okay. 0 here doesn't immediately mean the arithmetic 0 which we use in defining a number system. It obviously carries similar properties to the 0 we have, and indeed this symbol has arisen from the 0 we use in our arithmetic operations, but merely it's a symbol here to denote an element which has no effect on the element it's added with inside this non-empty set. Number three, for each element A in V, there exists an element B in V such that when you add B to A from either side, you get the additive identity back. Okay. We denote this element B as minus A. Okay. And number four is that for all elements A, B from V, A plus B is same as B plus A. So it's the commutative. It's the commutative operation. Right? Yeah. And in number three, I should add this, that this minus A value is called the additive inverse. The additive inverse of V. Okay. One more point I should add with a star here, that having plus as a binary operation, this typically means that for all elements A, B in V, A plus B is also in V. Okay, that is what the, so this property if listed separately, it's called the closure property. Okay, so suppose I name these properties as, say, G1, G2, this as G3 and this as G4, then this non-empty set V with respect to this binary operation plus is said to be an abelian group, if G1 to G4 is satisfied, or I should say provided plus is a binary operation. That is the closure property holds. Is a binary operation. Got it? Okay. So now suppose we have, now let V along with plus be an abelian group. let F be a field, let F be a field, then we define define for all elements C in F the following operation, So what is the operation given as? So number one, that if you multiply this element C with any element from V, then it's again in V for all elements A in V. Number two, if you have two elements, say C1 and C2 from the field F, you have an addition of them multiplied by any element A from V, then this distributes as C1A plus C2A for all C1, C2 in F and for all A in V. Number three, you have C1, C2 times A is nothing but C1 times C2A for all C1, C2 in F and for all A in V. For all C1, C2 in F and for all A in V. Next property is that number four. So C multiplied with any addition of the elements from V, say A plus B, then this is distributed as CA plus CB for all C in F and for all AB in V. And the final property is that 1 multiplied with any element A from V is equal to A for all A in V. Okay. So this operation is called the scalar multiplication. Okay. The operation C dot A to be precise, dot is the symbol of the operation, on V by the field F is called a scalar multiplication. If properties 1 to 5 holds. Clear? Okay. Therefore, so now we come up to the definition of a vector space. Let V be a non-empty set. Let plus be a binary operation defined on V, and V has a well-defined scalar multiplication with the field F, then this non-empty set V along with this field F, so it's denoted like this, it's called V over F, okay, along with this binary operation plus is called a vector space. The elements of V are called vectors, and the elements of F are called scalars. Okay, so that's the precise definition of what a vector space is. Now if I define what a field is, which I should do because I am assuming that this is just an introductory video. So what a field is basically. So what you have in a field is that, so suppose you have a non-empty set F. F is a non-empty set, plus I'm not getting too constructive here, plus and dot are two binary operations defined on F such that So we have these set of axioms. So consider them as, say, A1. A1 is for all elements A, B in F, A plus B, sorry, for all elements A, B, C in F, A plus B plus C is same as A plus B plus C. Second axiom is that for all there exists an element 0 in F such that 0 plus A is same as A plus 0 is equals to A. Again, this is here 0 is just a symbol to denote what an additive identity basically is. 0 is again an additive identity here. The third axiom is that for all, so this happens for all A, F. For all elements A in F, there exists an element B in F such that A plus B is same as B plus A is equals to 0. B is obviously denoted as minus A. And the fourth axiom is that for all A, B in F, A plus B is equals to B plus A, right? So obviously you can notice from here, because when we had defined the non-empty set V with respect to a binary operation plus, we had only these four axioms, right? So that is this non-empty set F with respect to addition forms an abelian group. This forms an abelian, right? So you have an abelian. Got it? Okay. Next we have these axioms. So M1. M1 is that for all AB in F, ABC in F, you have A dot B dot C same as A dot B dot C. A dot B dot C. So here dot is simply just a multiplication notation. Okay. The second axiom is that there exists an element 1 in F such that 1 dot A is same as A dot 1 is equals to 1 for all A in F. Again here 1 is simply a notation to denote what an multiplicative inverse is. So here 1 is called the multiplicative inverse. Multiplicative inverse. Third is that for all elements A in F, there exists, for all elements A in F, there exists some element B in F such that A dot B is same as B dot A is equals to 1, provided, or I should just add it up here only, for all non-zero elements A, this is satisfied. Okay. Let me just add it up here. So this is for all non-zero elements in F. Non-zero elements means except the additive identity. Any element is not the additive identity. So it equals to 1. B is denoted here as A to the power minus 1, which is our simple notation of inverse of an element, 1 by A. Okay. And it's called the multiplicative inverse. Okay, sorry, this is the multiplicative identity. Very sorry. And here you have the multiplicative inverse. And the fourth axiom is again that for all A, B in F, A dot B is equals to B dot A. Right? So if these four axioms hold, then observe on an analogous step as we proved for an abelian additive group. So F except the zero element, because here we have to avoid the zero element to have the inverse. So F except the zero element with respect to the operation dot is again an abelian group. So the terms used typically is that if you have a additive operation, it's called an additive abelian group. If you have a multiplicative operation, you have a multiplicative abelian group. Okay, and you have two more operations which are called D1 and D2. D1 is they are distributive properties. So it's that for all A, B, C in F, A dot B plus C is same as A dot B plus A dot C, and D2 is that for all A, B, C in F, we can distribute from either sides. That is A plus B dot C is equals to A dot C plus B dot C. These are called the distributive properties. Distributive properties. So basically what we have is actually that if you have a non-empty set F, therefore a non-empty set F along with two binary operations plus and dot plus and dot is called a field, if F with respect to plus, or I should just simply write it in words that if F is an additive abelian group, so obviously it has the zero element, so F except the zero element is a multiplicative abelian group, and F obeys distributive property with respect to plus and dot. Clear? So very basic examples of field would be R is a field, complex C is a field, Q is a field, are fields. We can obviously check all these axioms using them. Z is not a field. Z is not a field, and the reason is as you have 2 in Z, but 2 has no multiplicative inverse in Z because 1 by 2 is not in Z, which implies 2 has no multiplicative inverse in Z, right? Because 1 by 2 is not in Z, and 2 times 1 by 2 is same as 1 by 2 times 2 is equals to 1, right? So 2 has no multiplicative inverse. And this is actually the precise reason why R, C and Q are fields, because any element you choose, any non-zero element you choose from R, C and Q, they have multiplicative inverses. Every other properties are pretty trivial for these number systems, right? Because we know that our numeric zero, our numerical zero is simply the additive identity here, and our numerical one is the multiplicative identity in all these sets, right? So the only problem Z has is you do not have fractions in, or you do not have reciprocals inside. That is the only difference. Okay. So let's come to examples of vector spaces. Examples of vector space. So if you choose any field, then any field is a vector space over itself. It's a vector space where F is a field. And checking it is pretty obvious, right? Because since it's a field, so it's obviously an additive abelian group. Right? So the first criteria for a vector space is done, right? Further, since you are choosing elements from this F, say C, and you choose elements from this F, which are A, then CA will obviously belong to F, because this scalar multiplication is nothing but the usual multiplicative operation inside a field. So, and we know by the since F obeys the multiplicative property, or rather I should say, since F has multiplication as a binary operation defined on it, so this property will obviously hold, right? I guess it's obvious to notice, right? So you can check this, obviously this is pretty easy to check. Now you can find that C over R, R over R, C over Q, R over Q are all vector spaces. Are vector spaces. So you can, I would ask to check this as an exercise because this will actually help you to understand all the axioms you have. Okay. Number 3, let's say. Okay, one more thing I should be describing here, that you cannot have a vector space with the underlying field to be a extension field of that vector of the vector. That is, to be more precise, let K and F be fields such that K over F is a field extension. Right? That is that is F is a subfield of K. F is a subfield of K. Okay? Subfield in the sense means that it's a subset of K and is a field with respect to the same operations as K. Okay. Then F over K is not a field. Is not a field. And you can obviously understand this via an example, because if you choose this, let's say R over C, then you have I in, you can choose the scalar as I in C because C is the underlying field here, and you can choose the element 1 from R, let's say. Okay. Then I dot 1 must be in R for RC to be a vector space, because that's the precise definition of the scalar multiplication. But we know I dot 1 is nothing but I, and I is not an element of R. It's the imaginary number, right? Iota. It's in C only, right? Therefore, scalar multiplication closure does not hold in case of this set. So it's obviously not a vector space. Right? So you should have an idea why this happens. Got it? So on analogous steps, we can also show that if you consider the n tuple field Fn, then Fn over F is also a vector space. Is also a vector space with respect to component wise addition. With respect to component wise addition and component wise scalar multiplication and component wise scalar multiplication. That is, so component wise scalar operate is it's simple of this also. Suppose you have a1, a2 till an in F, plus you have say b1, b2 till bn in F, then that is nothing but a1 plus b1, a2 plus b2, and so on till an plus bn in F. So that's component wise addition, and component wise multiplication is if you have C from F, then C times a1 till an is nothing but CA1, CA2 till CA. Okay, so that's pretty easily understandable, right? Okay. Okay. Let us consider the next example. Example number 5. Let MNR be the collection of all real matrices of dimension n cross n, right? Then MNR is a vector space, with respect to matrix addition. With respect to matrix addition. So this is pretty easy to check. We will just go through the checking once. That is, obviously, if you have two elements, suppose say A and B are in MNR, then obviously A is of the form Aij. So I am not, writing the dimension here because we know that it's of dimension n cross n. So I ranges from 1 to n and j ranges from 1 to n. Right? And B is say of the form Bij, then we know A plus B is nothing but the matrix Aij plus Bij, and obviously that is again in MNR. So closure property holds, right? We know in matrix addition associativity is trivial, right? The zero matrix, 0n, which is the zero matrix, that is 0, 0, 0, all elements, all the entries are 0. That is Aij equals to 0 for all 1 less than equals to I less than equal to n, 1 less than equal to j less than equal to n, right? So it's this matrix. So it's the additive identity, right? Is the additive identity. Right? If A is in MNR such that we represent A as the elements of A as Aij, then B consisting of the elements minus Aij, component wise obviously, which we can also denote as minus A, is the additive inverse. Is the additive inverse. And matrix multiplication, matrix addition is commutative as well. We know that matrix addition is commutative because what happens in a matrix addition is we have component wise addition in the matrices, right? And each component is a real number. And since commutativity holds in the real number, so it will obviously hold in the matrices as well. Because see, what I'm actually trying to say is that so A plus B is of the form Aij plus Bij. But each Aij and Bij are real numbers, right? So it is obviously of the form Bij plus Aij, which is equals to B plus A. As each Aij and Bij are reals, right? So it's obviously a an additive abelian group. Matrix set of matrices with respect to matrix addition is an additive abelian group. And if you choose let C be a real number, then what is CA? So CA is the matrix CAIJ, right? If A is of the form Aij. And obviously since C is a real number and each Aij is a real number, so C times Aij is again a real number, right? Then CA is in MNR obviously because dimension is nowhere to change. And the other properties hold trivially with respect to matrix addition, right? Because if you have C1 plus C2 times A, so it is of the form C1 plus C2 times Aij. But Aij is a real number, so you can obviously distribute it. So it's C1 Aij plus C2 Aij, right? And C1 Aij is C1A, C2 Aij is C2A, right? Similarly, if you have C1, C2A, so this is C1, C2, Aij. C1, C2 and Aij all are real, so they are associative, right? So we can associate C2 with Aij. So it's C1 times C2 Aij, and it's nothing but C1 times C2A, right? Similarly, if we have C times A plus B, where A is of the form say Aij and B is of the form Bij, then this is nothing but of the form Caij plus Bij, right? So it's nothing but the matrix with entry Cij plus Bij plus Cbij. So it's Ca plus Cb. And if you multiply with 1 times A, nothing but 1 times Aij, which is same as Aij. So it's A. So therefore MNR is a vector space, right? MNR is a vector space. Okay. The other, okay, one more thing, let us just check. That is, let V be the collection of all symmetric n cross n matrices over R. Okay, is V over R a vector space? A vector space. So let's check this. To check whether V is a vector space, we need to again follow these axioms only. So that's quite easy at this moment, I guess, because if you choose two elements, say A and B from V, then we know that A transpose must be equal to A and B transpose must be equal to B because they are symmetric. And we know that A plus B transpose is nothing but A transpose plus B transpose from properties of transpose. So that is equals to A transpose is A and B transpose is B, right? So this is equals to A plus B. So uh, therefore A plus B is in V, right? We know that the zero n cross n zero matrix is symmetric because the transpose of the zero matrix is again a zero matrix. And if you have minus of A, and that is obviously a symmetric matrix as well, if A is symmetric, right? Because minus of A transpose is minus A transpose. So it's basically, so A transpose is A, so it's minus A, right? Therefore, minus A for all matrices A minus A is also in. I mean, associativity and commutativity holds trivially for matrices, so they will also hold trivially for symmetric matrices as well. Right? Hence, V is an additive abelian group, and since the properties of scalar multiplication will also hold trivially because they hold for all matrices, that is C1 plus C2 times a matrix A is equal to C1 times A plus C2 times A. Then C1 C2 times A can be associated as C1 times C2A. 1 times A matrix A is equals to A, and some scalar C times A plus B is CA plus CB. These properties holds for every matrices, and since the set of all, the collection of all symmetric matrices is basically a subset of the collection of all n cross n matrices, so these four properties will trivially hold. The only property which we actually need to check is that whether closure property holds or not under the scalar multiplication. So let A be in V and C be in R. So we know A transpose is equals to A. What is CA whole transpose? So CA whole transpose is nothing but C times A transpose. So this is equals to CA. So that implies CA is in, right? And you can obviously check it like this. That CA is basically, suppose we write it like this. So it's CA11, CA12. Let us consider a small matrix to be more precise. Okay. Suppose we consider the example of a 3 cross 3 matrix. Okay. So CA is of the form, say, CA11, CA12, C times A13, CA22, sorry, CA21, CA22, CA23, and CA31, CA32, and CA33. So CA transpose is basically this, right? So it's CA11, CA12, CA13, CA21, CA22, CA23. So it's CA31, CA32, CA33, which is nothing but C times. So you can see, obviously take C outside, so it's C times A transpose. Right? Therefore, V over R is a vector space. I guess it's clear. Okay. So if I will end this lecture with a definition of what a subspace is. Definition: let V over F be a vector space. Then a non-empty subset W of V is called a subspace of V if W over F is a vector space with respect to the same binary operations as defined on V. Clear? Example: for all vector spaces V over a field F, the zero set and the complete vector space V are subspaces, right? You can check obviously that zero forms a vector space on its own, and obviously since it's a subspace of V, you can obviously operate with the same binary operations as defined on V, and we know that every set is a subset of itself. So these two holds trivially. Subspaces called the trivial subspaces. Called the trivial subspaces. The immediate example we worked out previously, that is the collection of all symmetric matrices is a subspace of M and R, right? The other trivial examples are that the collection of so Q, we can consider it like this: Q over Q, it's a subspace of R over Q, because we need to keep the field same, right? Is a subspace of C over Q. And this is pretty obvious to notice because Q, R, and C, they are individually vector spaces over the rationals, and the operation, that is addition and multiplication, are our usual addition and multiplication, and they are same defined on Q, R, and C. So obviously this forms a subspace. Okay, and I often use this as the symbol of subspace. Clear? Okay, got it. So I will end this lecture with just a subspace criteria, the subspace criteria. How to check whether a given subset is a subspace or not, the subspace criteria. Okay, so a non-empty set W of a vector space VF is a subspace of V, if and only if alpha times A plus B belongs to V for all alpha in F and for all A, B, and V. Okay, so if you are given any subset, then you can obviously just use this criteria to check whether it's a subspace or not. Okay, so let me just go through an example. Okay, suppose you have this set. So example, suppose you have F equals to R3, the field, sorry, you have V equals to R3, you consider this non-empty set R3, and you consider the subset W1 of R3 as W1 is the collection of the elements U in R3 such that U is the 3-tuple of the form X00, right? So W1 is a subspace of R3. W1 is a subspace of R3 as for all elements C in R. R3, obviously we are considering R3 as a vector space over R. So for all elements C in R, what is C times U1? So it's C times X1 0 0, where U1 is of the form X1 0 0. Therefore C times U1 plus U2 is of the form C times X1 plus X2 0 0, where U2 is of the form X2 0 0. So U1 and U2 are elements from R3. So C1 elements from W1. So CU1 plus U2 is obviously an element from, for that implies CU1 plus U2 is an element of W, since C times X1 plus X2 is a real number, right? So therefore W1 is a subspace of, got it? So this is all about this lecture. I think I have pretty comfortably introduced the concept of how a vector space is declared. So I hope this helps in getting a prior knowledge of what a vector space is, what it looks like on a mathematical note. So yeah, so meet you guys in the next lecture.